So write a polynomial. So this is, for this test, it's going to be an extra credit question in the test. It won't even be at the end. You'll have a couple of those at the end as well, but I'll mark it as extra credit. And this is the complex conjugates theorem. So if a polynomial equation has real coefficients, and a plus bi is a root, then a plus bi is also a root. For example, let's just, before I go on with this, so let's say we have a graph, and sometimes the graph looks like this. Like this is a cubic equation. And when I say cubic, I mean it's got x to the third power, right? So I'm not sure what the rest of the terms are, but x to the third power is the largest degree. So the end behavior is down, up. It might have a squiggle in the middle here, but it has that behavior. So the solutions are where it crosses the x-axis. Well, you can see, here's what's weird. It has one real solution. It only crosses the x-axis once. But according to the fundamental theorem of algebra, there must be three solutions. And so the other two, well, it doesn't cross the axis. If that just had come down, a little bit lower, maybe if it looked like this, we'd have a couple more solutions there. But this particular graph, didn't do that. So what I recommend doing is, at this point, so the other two solutions must be imaginary. And what's real about complex or imaginary roots, what's interesting about those is that they always, always, always come in pairs. So complex or imaginary roots come in pairs. And this is what the complex conjugate theorem basically says. If a polynomial equation with real coefficients has, if there is an imaginary root, if there is one imaginary root, there must be a partner. There must be another imaginary root that's almost like it. Look how similar these are. One is a plus bi, another one is a minus bi. So if you had 2 plus 3i is a solution, then 2 minus 3i would also be a solution. So the imaginary solutions, the complex solutions, will come in pairs. And that's always going to be true. So this question says, well, okay, this is cubic, kind of like the one example I just showed. It's cubic. It means it has x to the third. It has three solutions. Unfortunately, they only give me two of them. They gave me 5. And they said one of them is 3i. But you kind of know the other one, don't you? I mean, imaginary solutions come in pairs. It's according to the theorem, if one of them's a plus bi, the other one's a minus bi. If one of them's positive 3i, the other solution in this case would be negative 3i. So those are my three solutions, 5, 3i, and negative 3i. They only gave me one, but you had to know those come in pairs because of the complex conjugates there. They always come in pairs. You'll never get one imaginary solution. You'll always get 2, or 4, or 6, or 8, an even number. Okay, so we're going to write an equation. So I'm just going to call this f of x. There's 3 solutions, so I'm going to write the 3 factors here. So let's just write out the 3 factors. This one will be x minus 5, right? X minus the solution. This one will be x minus 3i. And this last one will be x plus or minus negative 3i, which is x plus 3i. Now, just to put it in kind of standard form of a polynomial, let's FOIL these guys together. So we'll multiply the x minus 5 in just a minute. So you get x squared minus 3ix plus 3ix, that goes away, and then minus 9i squared. Now that can be simplified further because that's really x squared plus 9, right? Because I squared is really negative 1 there. And so then we're going to FOIL those two things together. So we get x squared times x is x to the third minus 5x squared plus 9x minus 45. So that is a polynomial equation of the function that has those roots there. I think there might have been a homework problem or two on that. I definitely have an extra credit question on the test on this. So if you want to, think about every time you see imaginary, they come in pairs and they look almost alike. And you can work backwards because each factor is always x minus the solution is a way of thinking that through to get the factors. Okay, that's it.